talk will be, okay, the original author was Seong Jin Kim. Okay, and now Professor Tomo will talk on his behalf, and the title, do you also change the title? Very good, very good. The same title. So it's a title about galaxies in the reionization epoch. Right, am I right? Yes, most like that. So let's welcome Tomo.
I'm sorry, I'm not Seong Jin Kim. He told me he's not feeling very well. Then he cannot come to ASROC. So then he asked me to give a talk for him instead yesterday. So I quickly prepared these slides, but I still want to do my best. I prepared these in a hurry, but I still want to do my best because I believe what Seong Jin is doing is very, very interesting. So I hope we have a chance to introduce his work to you. So Seong Jin obviously is here. And before starting, I want to thank all my collaborators. Those students work very hard. These guys reduce JWST data, almost by themselves. So that's a nice work. And also, the students at NTHU and also NCHU, Professor Hashimoto's group also helped us a lot. So I want to thank them all. Let's get started. Okay. So as you probably know, that JWST is revolutionary. Bring us a revolution on how the galaxy work. Compared to Hubble Space Telescope, 2.4 millimeters, JWST mirror is 6.5 millimeters, and that gives us 3 times better resolution, and then also, depending on the wavelengths, much better sensitivity. For example, it's depending on sensitivity, so here's the JWST. Compared with the Spitzer, depending on the wavelengths, but it's 10 to the 100 times better sensitivity. 2 orders of sensitivity improvement is the reason why it's bringing us a revolution. Okay, then this is a picture for the Hubble Space Telescope, and we are trying to push the frontier of the galaxy formation towards earlier and earlier to the beginning of the universe. And Hubble Space Telescope are doing good job to redshift 7 and 8, but this redshift 10 universe we never seen before JWST. Now because of JWST, we're starting to see this universe with redshift 10 or less than 500 million years from the Big Bang. And this is the area Seong Jin is interested. So Seong Jin is looking for redshift 10 galaxies, and with redshift 10 galaxies, we can do a lot of sciences because that's a frontier. We have never seen these galaxies before. But if I pick one of the Seong Jin's interests is this cosmic star formation history. So this is so-called Madalbrot, cosmic star formation rate density as a function of redshift, and then we never had the points here at redshift 10 before JWST, and then Seong Jin is curious about this area, how much stars the universe was creating at redshift 10. The data Seong Jin used is JWST Cosmos Web. So this huge area, 77 square arc minutes data was taken with JWST. So this is all JWST data. And what's nice about Cosmos Web is it's much larger area. Compared to earlier JWST fields such as shears or glass, it's almost 10 times larger field. And a larger field means we can search for rare, massive galaxies. So these are the Seong Jin's interests. These massive galaxies are difficult to find in small field. How do we find these galaxies? We find at 1.1 micron dropouts. Here is a simple distribution of method. So this is a galaxy SEV, typical galaxy SEV, redshifted to redshift 10. And redshift 10, galaxy's Lyman alpha break is already here at 1.5 micron because it's redshift to 1.5. So it's not visible in JWST's 1.1 micron filter, but it is very bright, 1.5 micron filter, and then other radar filter. So they define these galaxies as 105 dropout. To be more specific, Seong Jin is doing this. So he required object to be more than 5 signal detection in 1.5 micron, and then basically not detected in 1.1 micron because of the redshift. And then those are the galaxies. In this color diagram, those galaxies are come here. So the blue ones are good candidates. Okay. But as you can see, there are 180 galaxies here. There are so many candidates here. What does Seong Jin do? He does it eye inspection. So he looked at all 180 by eye and then carefully rejected the spurious candidates. Maybe that's why he's too tired and then he cannot come here. Anyway, so these are three of his good candidates that he selected. So here, this is Hubble eye band, and then 1.1 micron, 1.5 micron, and then beta bands. So these are JWST. Okay, and as Seong Jin required, so it should be detected in 1.5 micron. Yes, it's detected, right? And then it dropped out because it's high G. There's nothing here in blue bands. So these are good candidates. He found 6 of them, and he did the acid fitting. Acid fitting look like this. Let's look at one of them. So these 3 are JWST detection. So this is 1.5 micron. That's good. And then it's very important that it's not detected in 1.1 micron. So 1.1 micron, it's not detected. So that's why we know it's high G. And then he performed the acid fitting. So now he knows the redshift, photometric redshift, and the stellar mass, and the star formation rate of these galaxies. Let's try to plot it. So if we plot it, it looks like this. So these are his galaxies. So this is redshift and then stellar mass from the acid fitting. And as you can see, this is filling the empty space, right? So at redshift 10, such massive galaxies are not found previously. So first of all, this is all JWST data points, and then these earlier JWST works were from small field, so they found this massive galaxies, but not massive galaxies like Seong Jin. And this is very interesting. These mass, if you look at this is redshift 10, and then the mass is 10 to the 10th. This is amazing, and this is already inconsistent with the lambda CD. Well, this was pointed out by the previous paper, this LABE 23. This was Nature paper, by using these galaxies. But the Seong Jin kept finding massive galaxies 10 to the 10 at even higher redshift. So lambda CDM need to be able to explain these galaxies. If you look at the mass function, if you convert it to mass function, integrate the mass function, assuming the phase detail, then this value is going to come here at redshift 10. So previous JWST work from small field compared with this Stefano 21, and if you look at this, then it was like this, and maybe in terms of mass, stellar mass density, it might be quickly dropping towards higher mass. Okay. If you plot it the main sequence, so the stellar mass against star formation rate, it's got here, so main sequence, it looks like that there seems to be a galaxy main sequence at redshift 10. So, and then it seems to be a natural extension from high G redshift 6, and then here's redshift 6, and then maybe redshift 10, except this stuff. As far as I know, this is the first time galaxy main sequence was shown at redshift 10. Okay, let's get back to the first question of Seong Jin. Seong Jin's first question was Madal. What about the star formation rate density at redshift 10? And then he now has the answer. So his answer is here. So it seems his data is supporting the rapidly dropping model instead of this one. It seems rapidly declining star formation. Okay, and I want to take a moment to introduce other of our students' posters in this meeting. This is not, as a group work, and the other students are also doing a very good job. Jimmy created measure the cosmic summation rate density using mid-infrared JWST mirror to redshift 5. This is one of the key results of the JWST mirror. And then I am so proud that this key result came from a student paper in Taiwan. This is the JWST $10 billion project, right? And the key paper coming from Taiwan, I think that's great. So please have a look at the paper. COSAS found the protocluster at redshift 8.3. That's amazing. So please look at the paper. And COSAS also reduced the data, Cosmos data by himself. So big approach to him. Yuan one day walked to me and then he told me he found 20 brown dwarf stars from JWST data. I'm so surprised. Usually these brown dwarf stars with 600-700 Kelvin, very low temperature stars, people take many years to find one. He one day found 20, and then he didn't look surprised. So we look at what's that? Leah is also more challenging, trying to find 3 micron dropouts at redshift 20, and then she already found some candidates. So please go to our poster and look if it's true or not. And also Tom found very dusty galaxies from dusty AGMs from JWST. So please have a look at the paper. Okay, it's time to stop. So I summarized Seong Jin's discoveries. I'm really sorry that Seong Jin couldn't come here, but if you have questions, comments, please send it to Seong Jin's email. I stop here. Thank you very much.
Now, questions? Yes, here, please. Microphone, here.
Very nice talk. So yesterday there's a paper in the archive about the discovery of the Z14 galaxies, also JWST. So how does that one compare to those who found?
We are actually looking at 1.1 micron dropout, and redshift 14 is the next one, 1.5 micron dropout. So the selection method is a little bit different.
But I think the physical properties is that consistent with what we thought.
Sorry, I haven't looked at the details of that paper. I need to go back and then just take it.
Good. Other questions? Comments? The background.
Okay, good stuff. How much do you trust self-mission rates in stellar mass at this era using the CD model?
That's a good question. Star formation rate should be more okay, right? Because it's UV light and we're measuring UV light. But then stellar mass, as you said, we only have the UV photometry to estimate the stellar mass, so it's more uncertain. So it'd be nice to do a spectroscopy or very infrared observation. And it's actually, our samples are bright galaxies among JWST detection, so it's nice for the spectroscopy or for observations. Thank you. I was worried someone's going to ask about that.
Yes, here. One more question here.
So the Seong Jin has a plan to change it to computer, not by eye rejection.
Yes.
Yeah, the plan. So, I mean, the computer would make the data more reliable and more.
Yes.
Avoid to be so tired to come to the meeting.
Yes, that's a very good comment. It's unbelievable that we are relying our eyes in the 21st century. This is year 2024, this era of AI, and we are still relying on our eye. But then there are galaxies with a tiny detection. There are many of them, and it cannot be detected in computer. There are galaxies with a little bit of tiny detection here. There are many of them, and then in computer it's less than 1 sigma. So statistically it's not detection, but our eyes can see it, and then I know it's not a light galaxy, so we we just need to reject it by eye. And then it's actually customary, common procedure in this field. You have to reject many by eye. But I really agree.
Sounds like a very exhausting field. All right, so more questions and comments? Back there. Okay.
Thank you for a very nice talk. I was wondering if about the this is UV stock emission history. It's kind of up to limit, and we know that there's a significant fraction of stock emission from the subscripted dust. So does that affect the results between the rapidly declining and rapidly rising?
Yes, thank you very much for asking a very good question. So, yes, so here we are missing we are just using UV, right? So it's the dusty stop emission rate we are missing here. That's why this guy, this student, Jimmy, is using a mid-infrared to measure stop emission rate. And so his work should be free from this dust extinction program, but of course, our mid-infrared instrument is less sensitive, so he can only go to Redshift 5 instead of Seong Jin's Redshift 10. Thank you for the good question.
Okay, we are somewhat behind the schedule, but there was a question, right? So the last one.
Hi, Tomo, great talk.
Thank you.
So I wonder, is the result going to change if you search for other different fields in the selection companies?
So sorry,
So
if
in the
I
selection, after you search for a particular field for this candidate, and is the community going to change if you look for other area next time?
Okay, so one of the reason why I select this field is that because it's a large field, it's Cosmos, right? So it's the largest JWST survey field. So hopefully, if we choose galaxies from large field, then we are free from the cosmic variance, and then maybe we have more reliable, statistically more reliable result. That's the purpose in selecting this field. Thank you.
All right, let's move on and thank speaker Tomo again. Now our last talk